Swayam Prabha. Digital India. Educated India.
The next speaker is from Tokyo University of Agriculture and Technology in Japan. Ms. Shinatsu Ukawa is going to present. Thank you. She's going to talk about deep learning of high-frequency images for fault detection and chemical process.
Thank you for your introduction. Today I would like to talk about the fault detection method in chemical process using three-dimensional convolutional neural network and continuous neural network, continuous wavelength transform. And I'm going to divide my presentation into 4 parts. First, I will talk about our motivation. Secondly, a brief introduction to CWT and 3D CNN, and our method will be shown. Then I will show you 2 case studies, industrial data of groups with diction and Tennessee Eastman process. The result and the discussion part will follow after application of each case study. Last, I will conclude with a summary. So now, I would like to start by motivation. Fault detection and diagnosis plays an important role in monitoring chemical process, where it is expected to prevent severe accidents that cause emergency shutdown, financial loss, environmental disruption, and also human damage. Process monitoring starts with fault detection. Fault detection methods are divided into two types: model-based method and data-driven methods. Model-based methods depend on first principle modeling, which is generally difficult to perform because of process complexity. However, data-driven methods are established without a large amount of process knowledge and mathematical operation, due to which they have versatility in industrial application. Additionally, they are quicker to implement than the model-based methods. At the early stage of data-driven fault detection method, univariate analysis is applied to chemical process, but it couldn't find fault data because of the high correlated variables in chemical process. To find the valid fault data, multivariate statistical process analysis was adopted after univariate analysis. For instance, principal component analysis, partial least square, and support vector machine. These methods are widely applied in the industrial process now. But these above methods do not consider dynamics. In 1995, dynamic PCA was introduced as the method which can handle process dynamics. Equally, neural network-based methods have attention in many fields because of its flexibility for modeling complex structure and dynamics. Various neural network models have been proposed in chemical engineering fields, such as deep belief network, recurrent neural network, and long short-term memory, and also convolutional neural network. An important step in the establishment of data-driven method is pre-processing. A high detection rate cannot be achieved without an appropriate pre-processing method, even if the model possesses great ability. So far, frequency analyzing methods such as Fourier transform and wavelet transform have been applied to various fields and have exhibited good performance. Wavelet transform is expected to be applicable to chemical process data as it is more suitable at handling non-steady signal analysis when compared to Fourier transform. Despite the aforementioned fact, the pre-processing step has not been considered in many previous methods of fault detection for chemical process. In addition to it, information on time frequency domain has not been considered in most of fault detection for chemical process. Based on this fact, in our work, we propose the model fault detection method using 3D CNN and CWT. We transformed multivariable time series samples to time frequency scalegram by using CWT. And after this processing, we trained CNN, 3D CNN with scalegram as input. The output is a binary unit representing the fault or not fault. In the next slide, I'd like to introduce CWT briefly. CWT is a type of wavelet transform, which is a method to analyze features of signals. The wavelet transform has been said to be more suitable for non-stationary signals analysis than Fourier transform. It is widely used in various fields, such as fault identification for bearing, transient analysis, and also electrocardiogram analysis. Characteristics of the CWT are express original signals, to express original signals with mother wavelet, and to generate the scalegram by calculating scaling and time shift factor of mother wavelet for original signal. CWT performed two operations in the right figure: translation and scaling for mother wavelet. In the next slide, I'd like to show you how to make input data for CNN. At first, chemical process data is divided by a moving time window. Divided data is transformed into a scalegram by using continuous wavelet transform. We set the size of the scalegram to 20 times the size of moving time window when transforming. We perform this pre-processing for each variables. Finally, the shape of input data is 20 times the number of variables and the size of time shifting window. In the next slide, I'd like to explain about 3D CNN briefly. Here, brief introduction of 3D CNN is shown. We adopted 3D CNN for feature extraction and classification to handle much variable dataset. It is a logical extension of the two-dimensional CNN, which works with three-dimensional data like video, which has an additional temporal dimension in addition to the X and Y coordinates. CNN has been successful in image-based feature extraction and classification. 3D CNN was proposed for activity recognition, which requires temporal domain. Basic 3D CNN architecture is illustrated in this slide. The 3D filter is convolved with three-dimensional data to produce feature volumes. After subsampling and flattening, the feature are fed to fully connected layer for classification. This is an overall view of proposed method. First, the chemical process data was divided by moving time window. Divided data were transformed into a spectrogram using a continuous wavelet transform. We set the size of the spectrogram to, as I told you, 20 times the size of moving time window. during transformation. We performed pre-processing for each variables. And then finally, the shape of the input data was 20 times the size of moving time window times the number of variables. Next, the input data was fed into the 3D CNN, and the model was trained. After training, the output was a binary unit representing the existing of the fault. From the next slide, I'd like to show you two case studies. First of case study is the Tennessee-Eastman process. We use this to evaluate the ability of our proposed method using Tennessee-Eastman process was first introduced by Downs in 2013 and is based on a real process. It is widely used as a benchmark for evaluating fault detection and diagnosis method. The process flowsheet is shown on the right side. It consists of 5 main units: reactor, condenser, a compressor, a separator, and a stripper. For reactants and 2 products are included. It has 52 variables, including 41 process variables and 11 manipulated variables. We obtained the Tennessee-Eastman process dataset from the extended database published by Rees in 2017. Because the previous dataset is insufficient to train the CNN models. The structure is summarized in the table on the left side. This dataset includes data sample from 500 simulation run as training data of normal and 20 fault types operation mode. From another 500 simulation data, so from each simulation run, 500 data sample were obtained for training by 960 data samples were recorded for testing. Each fault was introduced to the process after sample numbers 20 and 160 for the fault training and fault testing. Next slide, we will move on to the result. This table shows the fault detection rate of the proposed method and the comparison method, PCA. PCA is the most widely used model for fault detection. The number of principal components was set to 9, and the confidence interval was set to 0.99. And Hotelling t-square and squared prediction error SPE were calculated for each fault. And we use evaluation indicator fault detection rate, and TP, FN, TN represent true positive, false negative, and true negative. The proposed method tends to improve the fault detection rate of fault, which PCA could not represent high performance. Then we selected fault 5 and considered the effectiveness of the CWT for feature extraction. Fault 5 was a step-like change caused by the condenser cooling water inlet temperature. It affected the variables surrounding the reactor and the condenser. We selected manipulated variables 10 and 11 from the process flow. Manipulated variable 10 was the reactor cooling water flow, and variable 11 was the condenser cooling water flow. They were located around the reactor and the condenser. The resultant scalegram are shown in the figure. They were They were selected for each of the test steps. The score graphs of each variable show different characteristics between normal operating condition and fault 5. This indicated the change of these process variables appeared in the time frequency domain. We believe that this difference implies the effectiveness of the proposed method for detecting faults. In next slide, I'd like to show second case study. The second case study is industrial data of loop with stiction. This dataset was introduced by Delari in 2010, and 93 types of data comes from various industrial groups, such as chemicals, pulp and paper mills, commercial buildings, mining, power plant, and metal processing. It includes from control, flow control, level control, temperature control, pressure control, analyzer control, and strip thickness or gauge control. To compare the performance of the proposed method, we prepared some of previous methods introduced in the book written by Delari. These previous methods have limitation on industrial application. For instance, some of methods can analyze short-length data, and almost methods are sensitive to noise and susceptible to the effect of non-stationary trend. Only 36 loops were found to which all methods are applicable. Our proposed method can apply to all of 93 loops. Before training the proposed model, we annotated each loop whether stiction occurs or not, based on the result of previous method and the comment of the book authors. Previous method shows different results on the same loops. One of them said the loops has stiction and others said no. So if 60% of previous method decided the loop has stiction, the loop annotated stiction as a result of previous method. If less than 60% of previous method decided to the loop has stiction, the loop annotated no stiction. After finishing the annotating by previous methods, we try to annotate by comparing the result of previous method and book author's comments. If the both result and comment are coincidence, the loop is labeled as stiction or no stiction and used for training of proposed method. If the both results differ, we didn't label the loops and use them as test data. Finally, 64 loops are annotated and 29 loops are not annotated. Here is the result. We evaluated by fault alarm rate and missed detection rate. We tried to make good models for this case study by sampling rate normalization and data augmentation, and also changing the window size and dropout rate. We constructed 12 models and got good result with model 6. It is no sampling rate normalization and data augmentation, and we set a window size is 40, and dropout rate is 0.5. We investigated the selection of appropriate window size is effective for achieving good performance. And also in this case, sampling rate normalization and data augmentation are not effective methods to improve model ability. This figure shows the output of the proposed 3D CNN fault detection models. From the left side, power plant, from the left side figure is shown power plant, and 2 of chemical process, and pulp and paper mills. Output values are plotted on the vertical axis, and sample number corresponding to the time is on the horizontal axis. The proposed method can show the point that the process deviate from normal condition. Previous method cannot show the time series result, but the proposed method can visualize the proposed condition on time. Additionally, we can set the threshold after making models to decide that the model has diction or not. I hope that it is useful to make flexible models for various applications. In the next slide, I would like to conclude this presentation. We proposed a fault detection method for chemical process based on CWT and 3D CNN. To evaluate the proposed method, we applied the model to 2 case studies. One of them is Tennessee Eastman process, and another one is industrial data of loop with diction. In first case study, the proposed method performed well on fault detection of Tennessee Eastman process faults, and we can find the proposed method captures a feature in the time frequency domain of process data. In the second case study, the proposed method was also applied to industrial data of loops with diction and show the validity. And the proposed method shows when the process deviates from normal condition on time. So that's all of my presentation. Thank you.
Okay, thank you. Do you have questions or comments? Yes.
I have one or two clarification I wanted to ask, and I have one or two questions. So one thing is when you're preparing the data for inputting 3D CNN your network, so how is the number of channels for the input image is equal to the number of features which you have in your data set?
I'm sorry, but I don't follow your comment, so please say that.
Yeah, I'm saying that you have an input data which has some features for predicting the fault, and then you are creating out of that you are taking the your CWT and then converting into the image, 3D image, where you have image and then you have number of channels for the image.
Yeah.
Okay. Okay, maybe we can talk offline for this.
Yes, please.
Yeah.
I'm sorry.
And then how did you decide upon the window size and the moving window size? Is there any method did you employ to determine the window size and the sliding window size for your data?
In this case, about Tennessee Eastman process, it is sampling time is 3 minutes, so maybe I think I think 20 sample. I said the 20 window size is 20, and it says 1 hour length.
Okay.
So I think it is it is a good for the process, this chemical process.
You use the 2 numbers. One is for 20 window size, and the other one is 40
20.
window size. Do you have any? Yeah. So what's the heuristics? How do you choose the window size?
Yes, I tried to sum of window size and I check the accuracy, and I choose the best. I choose the window size with.
Means, did you check what is the frequency of the fault occurring in your data set, and then you correlate it with your choice of the window size?
I didn't check the frequency of process data, but
Okay, we can talk offline. Last question.
Okay, thank you for your presentations. If I understand correctly, your model can classify whether the data is a fault or the normal. So, is there some additional prediction index, like which type of fault is occurred, or how much probability that the expected fault is the real fault or the normals or something?
your question is how to decide the threshold?
The question is that is the model just simply classify the data as fault or the normals, or did give any additional explanation about which types of fault or the how much probability that this fault is a real fault or not?
Okay. I'm now working on the fault, not only the fault detection but also fault identification. So maybe it's I work on the Tennessee system process, but it is some faults. Our proposed method can some faults can detect, but some faults cannot detect.
Cannot be detected.
Yes.
So maybe you had a plan to extend these methodologies to
Yes.
identification of the fault, or?
Yes.
Okay, thank you.
Okay, let's thanks to the speaker again. Thank you.